right, so by popular demand, we're going to go more in depth into the Serre spectral sequence next. And some good references for this are Hatcher's chapter on spectral sequences, Mosher and Tangora's chapter 8, and McLeary, I don't remember what section it is. So in order to talk about the Serre spectral sequence, I need to talk about a Serre fibration. So we'll call a map P from E to B, so this is a map of spaces. This is going to be a fibration, or more specifically a Serre fibration. I'll mostly just say fibration since this is the only kind of fibration we want. If it satisfies, well, it's going to have the homotopy lifting property. And specifically for finite CW complexes. So what does that mean? Well, if I have some X, a finite CW complex, then anytime I have this commuting square, where I've got P here on the right, and here this is going to be the inclusion at 0 into X cross I, then I should have a lift. So that means there exists a map here, making the diagram commute. And this is called a Serre fibration. If it was a Hurewicz fibration, in case you've seen that, studying maybe model categories or something like that, then this would have the homotopy lifting property for any space. So saying it's a Serre fibration is saying we're living in the world of CW complexes. And specifically, we just test against finite CW complexes. Okay, and so then some terminology. This B we call the base. E is the total space. And if I have some point in B, then I can look at its preimage in the total space, and this is the fiber over that point. And in general, if B is nice, really I just need path connected, though often in this world we'll want simply connected, as we'll see. Then anytime I look at the fiber over some point, it's going to be homotopy equivalent to the fiber over some other point, so I'll call all of those F. And then I just call it the fiber. So anytime I write that the fiber is F, I mean we're in this nice situation. Okay, great. So then you might remember from your algebraic topology course that given some fibration, so I'm going to write F to E to B, and the fact that I'm writing F here sort of implies that my B is path connected so that F is well defined up to homotopy. You may not have seen this for fibrations in general in algebraic topology. Maybe you saw it for fiber bundles or for covers or something like that. But in any case, in this generality of a fibration, then as long as pi 1 of B acts on F. Getting ahead of myself up there. Okay, so there's an action here, and an action comes up in the same way that pi 1 of some space acts on its universal cover by deck transformations. So you can look in Hatcher for more about that if you like, or if it's unfamiliar. But the upshot is that then pi 1 of B is also going to act on any homotopy invariant. So say on the homotopy of F, on the homology of F, on the cohomology of F. And in fact, that leads us to something called homology or cohomology with local coefficients, which we usually draw with a sort of scripty H. And this is just where you consider the homology of F in this case, or cohomology if you like, as a z-adjoin pi1b module. Okay, and at least for now, most of the time I'm going to try to avoid dealing with local coefficients. But if this is something unfamiliar, then I definitely recommend going back and reading that brief section in Hatcher. So then hopefully another familiar proposition is that given a fibration, or again, maybe you saw this for covering spaces or fiber bundles, oops, okay, you get a long Zech sequence in homotopy. So that looks like pi, oops, turning into a mess here. I think I need to move this up is my problem. Okay, so we've got pi n of the fiber, maps to pi n of the total space, maps to pi n of the base, and then our connecting homomorphism wraps around and we get to pi n minus 1 of the fiber, and so on. Okay, so great. So these are just some reminders about things that we know about fibrations. We get this nice long Zech sequence in homotopy. That's sort of one of the best things they can do for us. But now that we have spectral sequences, we've actually got a lot more. So this theorem is really the Serre spectral sequence that Serre constructed in his thesis. And maybe it's worth mentioning because this can be a point of confusion when there are so many spectral sequences with so many names. This is also called the Serre spectral sequence because Leray and Serre were the first to construct spectral sequences, and their work is related here. Okay, but for brevity, I'm just going to say the Serre spectral sequence, especially since it does appear in his thesis. And so this is going to work for fibration, so let this be a fibration. Notice that means that I've got this nice F, and in fact, I want to assume that F is not just well-defined up to homotopy, but is connected. So I've got this connected fiber, and this is really implied in the notation, but B is going to be path connected. Let's also take some abelian group. So let A be an abelian group. And what does Serre's spectral sequence theorem say? It says there's a spectral sequence. So the claim is that there is a first quadrant, which remember has our best kind of convergence. Let's say first quadrant homological spectral sequence. And it's going to look like the E2 page is described. So as we've already seen, this should be the homology of the base, actually with local coefficients in the homology of the fiber, with coefficients in whatever abelian group A you're working in. And that should converge to an associated graded for the homology of the total space with coefficients in A. Okay, well, most of the time I sort of want to avoid this local coefficient issue. So if B is simply connected, which just means that pi1 is 0, or maybe even more generally, maybe pi1 is something interesting, but if it acts trivially on the homology, then the form that we usually see for the Serre spectral sequence and is more commonly used, except in group homology, is, that we have the E2 page is the homology of the base with coefficients in the fiber, and then maybe in some abelian group A. And this cooks up for us an approximation of the homology of E. Okay, and so this is sort of what you more commonly see, but technically we do sometimes have to deal with local coefficients in this setting. Okay, there's not just a homology spectral sequence. I think we've even already talked about that. So there's also a cohomology version, and I'll just write that down. So we also have a first quadrant cohomological spectral sequence, and that's going to look like the same thing, only cohomology everywhere. It's almost not worth writing, but I like to be complete. Okay, so now these are local coefficients in the cohomology of the fiber, and this should cook up for us the cohomology of our total space with coefficients in A. And of course, if pi1 of bx trivially, then we get the nicer statement where we can ignore local coefficients, and we just have the cohomology of the base with coefficients in the cohomology of the fiber, and that cooks up for us the cohomology of the total space. Okay. This is really more about my notes and having this for completeness, but a little bit more interestingly, not the sort of just the same as the homology version, is that if we also know, whoops, I don't know if you can hear my cat crying in the background. She's very upset that I've locked her out. So furthermore, if A is a commutative ring, then we know the cohomology is also going to be a ring, right? It's a differential graded algebra. And so this cohomological spectral sequence is going to be a spectral sequence of algebras. And that's really extremely useful. So we'll often make use of the algebra structure here to sort of compute differentials. Once we know one differential, it'll propagate to many other differentials, and we'll see some examples of that shortly. Let me make one more note here, which is that if K is a field, then this E2 page is just going to be the homology of the base with coefficients in A, tensored with, sorry if I said homology, the cohomology of the base with coefficients in the field K, tensored with the cohomology of the fiber with coefficients in K. This is just coming from the Kuhn theorem. There's no Tor terms, right? And here we're tensoring over K. And remember, this is a tensor product of graded rings. So the usual thing. And in fact, the Kuhn theorem, to get this sort of nice version where we just have the tensor product, we really just need one of these to be a free K module. So let me write that. And then we won't have any Tor terms. So often what happens is our E2 page looks like this nice tensor product, and then we cook up something about the cohomology of the total space. Now, actually, as we'll see in some examples, sometimes we'll want to work backwards. So maybe we know the cohomology of the total space, and we'll cook up something about either the base or the fiber. So we'll look at some examples of that coming up shortly. But before we do that, I want to give you kind of just a quick idea of where this spectral sequence comes from. And I'll stop this video and do that in the next one.